Welcome to AI for Good, the leading United Nations platform on artificial intelligence. Organized by the International Telecommunication Union, the United Nations Agency for Digital Technologies, in partnership with over 50 UN agencies, and co-convened with Switzerland. The mission of AI for Good is to unlock AI's potential to serve humanity. As a multi-stakeholder platform, AI for Good advances solutions, standards, and skills. In today's AI for Good event, we are counting on you to use the live video wall feature to ask questions and post comments to help create an engaging session. Boost your AI skills and elevate your career with the AI for Good Discovery Badge. Receive verified digital credentials that recognize your engagement in cutting-edge sessions, exploring how AI is being used to tackle global challenges. To see if a session is eligible, look for the blue badge banner on the right side of the video interface that activates at the end of each live session. Share your badge on LinkedIn and across your professional profiles, and check the AI for Good events webpage for upcoming eligible online sessions. Discovery Badge sessions are part of the AI Skills Coalition, ITU's global initiative to strengthen credible AI learning pathways and expand access to high-quality, trustworthy AI knowledge worldwide. We encourage you to stay until the end to chat, connect, ask questions, and network with our distinguished facilitators and world-class AI experts in the neural network. It is now time to kick off the session and welcome our first speaker. The floor.
Thank you, Anna, for introducing the session. A very good day to everyone. Thank you for joining. Welcome to AI for Good's AI and Machine Learning 5G webinar. My name is Jiaying, the moderator from ITU, the International Telecommunication Union. So today we are going to have another exciting webinar. In fact, this is the ending webinar for the challenge that we launched several months ago, titled the Wireless Foundation Model, Empowered Synesthesia of Machines System. So during this webinar, we would like to invite our speakers, our colleagues from Peking University, the host, to recap on the problem statement, and we'll also invite the winners to present their solutions. We have proudly invited our 3 winners to present their solution each. And by the end of this webinar, we will have our guests from Peking University's Prof. Tsai and also Prof. Cheng to give out the prizes and also the certificates for the winners. So if I may pass the baton to Boxun already to recap on the problem statements and walk our audience through the problems and the challenge that you're working on. Thank you. Boxun, the floor is yours.
Okay, thank you, Jiaying. I will share my screen. Can you see my screen?
Yes, please go ahead.
Okay. Hello, everyone, and welcome to our AI for Good webinar, the World Ceremony for the Synesthesia of Machines, SoM Challenge 2025. And my name is Boxun Liu, and I'm a PhD student at Peking University. Joining us today are my partner speaker, a PhD student Xuanyu Liu, and Professor Xuesong Cai and Professor Xiang Cheng. And we are both from the Pervasive Connectivity and Networked Intelligence, the PCNI group from School of Electronics, Peking University. And here we would like to express our sincere gratitude to the ITU for providing this volleyball competition platform, and our special thanks to the Huawei for its generous sponsorship of the press awards. In this webinar, I will first provide a brief overview of the SoM Challenge 2025. And then the top 3 winners will present their solutions, and finally we will proceed to the awards announcement. First, I will explain what SoM is. As we all know, the integration of communication with intelligence and sensing is a key development trend for 6G. Against this background, our group has proposed the concept of SoM, Synesthesia of Machine, a novel paradigm for AI-native intelligent multimodal sensing communication integration. Inspired by the phenomenon of human synesthesia, SoM aims to explore the reciprocal mechanisms between the wireless communications and the multimodal sensing information. Some research covers the following 5 main aspects as shown below. This challenge mainly focused on the third one, the SoM enhanced transceiver design, that is AI native multimodal sensing aided wireless physical layer design. Previous studies on AI-enabled physical layer design have mainly focused on the task-specific AI models. However, these models face several limitations, including the limited performance, the poor generalization, and the fragmented design, making them unable to support the SoM-enhanced transceiver design effectively. In this context, wireless foundation models have emerged as a new paradigm for wireless physical layer design. Specifically, they refer to the models that are pre-trained on large-scale and diverse wireless data, typically in a self-supervised manner, and can be adapted to a wide range of wireless tasks through few-shot or even zero-shot learning, often outperforming the task-specific models. And our previous work, WiFo, is a pioneering study in this field. It was the first to bring the wireless foundation model paradigm to channel prediction and demonstrated impressive zero-shot performance. To further unlock its potential for efficiently enabling a wide range of CS-related downstream tasks, we launched this challenge to attract broader attention from research community. Specifically, we consider the 3 tasks in SoM enhanced transceiver design, namely channel estimation, loss or unloss classification, and vision-aided wireless localization. Our scoring considering both the task-specific performance and the model practicality with a particular emphasis on parameter-efficient fine-tuning. The key milestones of our webinar are listed here. Thanks to the attention and support from the community as well as the ITU AI for Good platform, our challenge has garnered over 150,000 views and attracted 39 teams from China and abroad to participate. Next, let's invite the top 3 winning teams to present their solutions. First, I will invite the team Zero Grid from Beijing University of Post and Telecommunications. Please share your screen. The floor is yours. I will stop the sharing. I can't hear you.
Sorry, we can't really hear you. While we wait for colleagues from Zerograd, maybe Boshun, is it possible or is it okay for you that we change the order?
Okay.
Is it sorry, Zerograd. Maybe you would like to try again, and if not, then we
可以听到吗？
yes.
yes, okay, good.
Okay,
Please go
okay.
ahead. We will keep this order, please. Yeah.
Hello everyone. Our team is Zero Guard. My name is Yongji Zhang. Please allow me to introduce our work. First, we introduced a parallel adapter structure. Compared to traditional series versions, the parallel branch better preserves the origin feature through the WiFo backbone, allowing contamination of general knowledge during fine-tuning. This allows the model to achieve performance close to 4-parameter fine-tune with minimal parameter updates. Secondly, we reconstructed the task-specific head by replacing traditional layers with 1x1 convolutions. This not only enables small, flexible cross-channel feature fluid, but also provides scalability for introducing large receptive fields in the future. Regarding the training strategy, we employed warm-up combined with causing annealing. The warm-up phase prevents gradient creation caused by randomly initialized components, while causing annealing ensures the model coverage is finite to the global optimal solution in the later stage. To further enhance the training scalability and efficiency, we formulate a strict parameter freezing and hyper-parameter opportunity strategy. We adopt a freeze backbone target captive approach by freezing the backbone weights. We ensure pre-trained knowledge remains in fact. We not only unfreeze 3 core components, the adapter for task adaptation, the linear norm for distribution alignment, and the task head for final output. This strategy significantly reduces memory footprint and computational overhead. Finally, we utilize the random search scripts to optimize key hyperparameters such as learning rate and weight decay. Through this systematic search, we indefinitely the most robust parameter configuration, ensuring both the reproducibility and state-of-the-art performance of our results. Next, my teammates will introduce their work.
Yongji, may I come in? So I assume that, okay, I can see the screen now. Please feel free to elaborate further the solutions that you provide.
Okay, thanks for Yongji Zhang. Hello everyone, my name is Haoxuan Xu from Zero Grade. Since our project covers 3 distinct tasks, I'll be taking over for task 2, which focus on the line of sight and non-line of sight classification. My goal was to design a high-precision downstream classifier while keeping the model extremely lightweight for real-time processing. Specifically, we built a dense connection chain, and we used a bench-norm GLU convolutional structure with chain-node concatenations. This ensures that the CSI features are reused effectively across the network. To strictly control the model size, we used a very small growth rate of 12. And we also applied dual-stage compression. First, our initial bottleneck shrink the 512-dimensional features down to 40. Then the transition layer for the refined data using polling. This keeps our computational cost at a minimum. And moving to our optimization strategy, we choose GLU activation. because it provides a smoother gradients for the complex CSI compared to the standard value. For the output, we designed a 3-tier layered classification head. It progressively reduced the hidden units from 32 to 16, and finally to 2. This creates a very smooth transition for the classification logic. Finally, by integrating dropout and bench norm, we ensure that even with only 0.03 million trainable parameters, the model is stable and generalizes perfectly, achieving a 100% accuracy score on the test data set. Thanks, and now I'll pass it over to Jianxiang Liu for text 3.
Thanks, Hao Xuanxu. Hello everyone, my name is Jianxiang Liu. I will taking on the task 3. First, introduce model lightweighting and multi-modal feature fusion. First, we use mobile VIT as a visual encoder. Compared with ResNet, it combines the efficiency of CNN with the global modeling ability of transformers, so it can capture global spatial information with few parameters. Second, for multimodal fusion, we use lightweight gate fusion instead of simple concat, because concat is a rigid fusion that fails to account for varying feature qualities across modalities. Finally, we direct predict the x and y. The model learning the general physical space, mapping multi-mode CSI and IGB features. Second, we introduce parameter efficient fine-tuning and training stability. First, LoRa. We use LoRa to fine-tune the pre-trained WiFo model. It only adds a small number of trainable parameters, so it can adapt the model to the localization task. We also use layer norm to improve training stability. Last is generalization enhancement and physical distance optimization. First, we apply data argument to both modalities. For CSI, we add random scaling and ghost nodes to simulate real wireless interference. Second, for IGB images, we use lightning and waypoint and blue changes to reduce overfitting. We also use a joint L1 and L2 loss. L1 helps keep training stable, while L2 helps the model fit the physical coordinate more accurately. Overall, our math improves efficiency, stability, and accuracy. That concludes my our presentation. Thank you very much for your attention.
Okay, thank you. Thank you for your wonderful presentation. And next, we invite the team Excellent from Zhejiang University to begin their presentation.
Could you hear me?
Yes, I can hear you and see see your screen sharing.
Okay. Good evening, everyone. My name is Xinjia Wang, and it is my great honor to present on behalf of Team Excellent. Today, I will share our technical solutions for the Synesthesia of Machines Challenge 2025. Our defense will focus on the design of lightweight, high-precision algorithms for integrated sensing and communication. Our presentation covers 5 key sections. I will first introduce the background and analyze the tasks. Next, we will detail our parameter-efficient fine-tuning solution. Finally, I will present our results and summarize our work. Let's start with the background. Traditionally, wireless communication modules are totally separated. This old approach causes poor generalization, struggles with sparse data, and creates huge overhead for base station. The SoM framework changed this completely. It uses our unified neural network to process inputs from different sensors at the same time, much like human synesthesia. In this new setup, wireless signals do more than just send data. They act as tools to perceive the environment using CSI. This slide illustrates the SoM framework. Just as humans combine different senses, we want to give machines the same ability by fusing data from cameras, lidar, and communication units on devices like autonomous cars or robots. We build a strong multi-modal foundation. This directly supports an AI-native system capable of complex perception tasks like localization and tracking. To make this work, our approach is built around a pre-trained model called WiFo. Architecturally, WiFo is inspired by the Muscat Auto Encoder Transformer framework, which you might know from computer vision. It leverages a huge amount of unlabeled NGPP-compliant CSI data and uses self-supervised pre-training to learn general spatial, temporal, and frequency traits of signals. WiFo takes complex channel prediction problems and turns them into a standard Muscat reconstruction task. This gives us an incredibly solid backbone network to use for the computation. Here are the 3 tasks we tackled. First, channel estimation. We've input sparse palettes to reconstruct a complete CSI tensor. The challenge is guessing the missing multi-path details, evaluated by NMSE. Second, loss-unloss classification. Using a 2D CSI example, we predict the link status. This requires extracting deep features from noise, measured by the FE score. Third, vision-aided localization. We fuse CSI and RGB images to pinpoint the user's XY coordinates. The hurdle is dealing with visual occlusions, evaluated by MAE. Starting with task 1, our core philosophy was parameter-efficient fine-tuning, or PEFT. Specifically, we heavily relied on layer norm tuning, which is an efficient fine-tuning strategy that enables the model to rapidly adapt to the channel distribution of a dataset by adjusting only the weights of the layer norm layers. within the transformer architecture. Additionally, we fine-tuned the WiFo's output head, so it can map the data back to the correct signal space dimension. This highly efficient approach successfully reduced our NMSE from 0.123 to 0.056. Moving forward, we think using techniques like LoRa could improve this efficiency even more. For the task 2, classification challenge, we maintained this parameter-efficient approach. Directly flattening WiFo's latent representation causes a loss of local structural information and inflates the parameter count. To resolve this, we paired LN tuning with a 1D CNN adapter. This 1D convolution filter slides over the sequence to aggregate features across tokens. It's really great at catching sudden changes in the signal that happen when an object blocks the line of sight. Then we use a simple lightweight MLP to make the final prediction. This pairing of a frozen backbone and a targeted adapter achieved 100% training accuracy and a robust 96.6% accuracy on the test set. For task 3, vision-aided localization, we adopted a fundamentally different approach. Since deep learning models often overfit to background noise, we opted for a rule-based algorithm grounded in strong geometric priors. Because the camera is fixed, we observed that there is a clear linear correction between the image, the detection results, and the actual physical coordinates. We utilized the pre-trained ULV-bar model to extract detection boxes for the target vehicles. Given that the target vehicle's Y coordinate remains constant, we filtered out redundant boxes and retained only the most accurate detection along that track. Finally, we applied linear regression to predict the X coordinate. This training-free method achieved an outstanding positional accuracy of 0.11 meters. This slide summarizes our performance across all tasks. For task 1, we tuned just 0.15 million parameters, yielding a score of 0.944. For task 2, we tuned about 0.19 million parameters for a score of 0.966. Finally, for task 3, we tuned 0 parameters and achieved our highest score of 0.987. In conclusion, we secured excellent overall performance with minimal parameter tuning. To conclude, a signal wireless foundation model can effectively replace fragmented task-specific fine designs. Furthermore, our approach robustly handles data sparsity, multi-modal alignment, and hardware limits without sacrificing performance. Moving forward, the ultimate solution of integrated sensing and communication lies in combining the representational power of foundation models with strict physical and geometry priors. Thank you for your attention.
Okay. Thank you to the team. Excellent for their excellent presentation. Next, let's welcome the team Tant X from the University of Electronic Science and Technology of China. Please go ahead.
Can you hear me?
Yes.
Okay, so let me share my PowerPoint. Let me. So good evening, everyone. This is Hao Tai from Team 10X. It's a great pleasure to be here today to share our journey in the SoM 2025 competition. Our work focuses on integrating wireless signals and visual information and using deep learning to help machines better understand the physical world. Let's dive in. Our presentation is divided into three main parts: a brief competition overview, second, our core mission design, and finally, the results display and our vision for the future. So what is this competition all about? It is centered around integrated sensing and communications, or ISAC. The goal is to move beyond just transmitting data. We want machines to actually perceive the world. By fusing wireless channel state information, which I'll call CSI later, with visual images, we aim to enable machines to perceive the environment in a more human-like way. The judges expect three things from us: multimodal fusion, model applications, and lightweight and real time. The heart of our solution is the WiFo model provided by the committee. Think of it as a signal translator. The data flow is simple yet powerful. We take sparse, noisy, raw CSI as input, and then we use the transformer encoder, performs global self-attention to extract deep spatial and frequency features. And this is where the understanding happens. Finally, the transformer decoder maps these hidden features back to the physical space, outputting a dense, reconstructed CSI tensor. Now that
Hello,
we've
hello.
introduced the Wi-Fi
Sorry to disturb. Would you mind going into presentation mode instead of this presenter mode? We can see your. Otherwise, you
okay,
just.
I'm so sorry.
No. Yeah, otherwise, you just.
Just
I think this will be okay. If you
okay.
cannot
Let me
change.
just.
Super, good.
Okay. So task 1, reconstruct complete channel state information based on sparsely distributed pilot signals. So we can see from the graph left and right, we can see the subcarriers from like 14 to 60. So we reconstruct from the sparse data to the whole data. And task 2, analyze channel state information samples to determine the scene type, loss or unloss. Is a classifier task. And task 3, estimate the target's position by comprehensively utilizing wireless channel information between the base station and the user's device, as well as RGB images captured by the base station. And then our mission design for task 1, we design a fine-tuned layer that maps the decoder's feature dimensions to twice their origin size. Use the ReLU activation function to enhance nonlinear feature representations. And finally, map them back to the original patch space. But after rigorous testing, we found that WiFo's pre-trained decoder was already so powerful. So we directly using the pre-trained decoder head included with WiFo, and leveraging the model's robust performance, we achieved accuracy comparable to that of a fine-tuned model while significantly reducing the number of fine-tuning parameters. And for task 2, we based on the high-dimensional dense features output by the WiFo-based model, we designed a two-stage fine-tuning architecture. Layer 0 used two one-dimension convolutional layers with a kernel size of 5 times 5. Layer 1, we use a lightweight linear layer that maps feature to a two-class probability. And finally, for task 3, we use a lightweight ULOV8 model for object detection. And then we use our random sampling consensus algorithm to match the trajectory of XY. And this is our results display. Task 1, our accuracy 0.910, and I think our trainable model parameters is very low. It's 0.24 million parameters. And looking ahead, we see three paths: semantic level, deep integration of visual and wireless signals, multifunctional network extension based on the WiFo-based model, and lightweighting and real-time evolution at the edge. In conclusion, our project demonstrated that a foundation model like WiFo combines with smart, light-weighted task heads is the future of ISAC. Thank you for your time.
Thank you. Okay, I'll share my screen. Thank you to all teams for their wonderful presentations. Now let's move on to the award announcement. After highly competitive contest, the final results have not been officially announced. Next, let's invite Professor Tsai to present certificates to the winners who placed fourth through sixth.
Okay, yeah, thank you, Bushun. I'm very honored and very happy to announce the awards today. So first, let's congratulate Team Cui Cao, right? For finishing this competition in sixth place. Congratulations. And should we go to the next one?
Okay.
And the Team Awesome, they win fifth place in this competition. So congratulations. And the next one. The first place is Team Kate. So congrats. And our second runner-up is.
Okay, thank you, Professor.
Okay.
Let's invite Professor Chen to present the certificates to the top three teams.
Okay, thank you, Bushi. Could you please move to the third prize? Right? No, not this one. It's the next one. I think it's a fourth. It's fourth place for the competition.
Third.
Or maybe yeah, yes, this correct one. Yes. So it's really my honor and pleasure to announce the third prize of this competition goes to the Team Zero Grant. Congratulations. And for the second prize of this competition, Boxing, could you please move to the next page?
Yes, a second.
Yes, the second prize goes to the Team Excellent. Congratulations. And finally, the first prize, goes to the Team TNHX. Congratulations. So well done. Okay.
Okay. Thank you, Professor Chen. Thank you, and congratulations to all the award-winning teams. The complete evaluation results are shown in this table. The top three teams will share the total price of CHF 4,000, and all certificates and prize payments will be delivered to the teams as soon as possible after the webinar. And finally, do you have any questions about the participant solution presentations? Please feel free to ask.
Okay, but I'm not quite sure. Shall we take photo together? I'm not quite sure.
Not necessary. Yes.
Yeah, but
yes.
If all the the winner can open their camera, so we can take together.
Okay. Yes, we can all open our camera to take a photo together. Yes, everyone. Yes.
Okay.
Can everyone share your screen?
Yeah. Okay, if okay, so everyone please open the camera so we can,
Yes,
you know,
open camera, yes.
Yes,
yeah.
Boshin, maybe you would like to go back to the certificates for each team, and then we take a screenshot for everyone. Yeah, I
Okay,
think they will
okay.
be
Yes.
nice. We can go to the
Yes.
first top three teams who are
Okay.
currently here, and then we invite them to switch on the camera, and then we take a screenshot for everyone. Thank you so much. Super. The teams you would also like to take your own screenshot. Maybe we move to second prize.
Okay.
Amazing. Super. Shall we move to first prize? Very cool. Okay, thank you so much. I hope teams you also took your own screenshot with the prizes. And also thank you very much, Prof. Chung and Prof. Sai, to take your time for this certificates distribution. Thank you for taking your time. Maybe, Boshin, we can move to the Q&A session. I already see that my colleague Vishnu is ready, and I think he has already posted one question for everyone. I think this is a question for everyone to consider. He is asking what are the fine-tuning optimization techniques that has been used for all the teams when you're competing and also finalizing these tasks. I don't know, maybe Vishnu, you would like to jump in and for the questions. And colleagues for all the teams, please feel free to express your views on this. Thank you so much, Vishnu. Floor is yours.
Thank you very much, Sheng. It will be good to have audience questions as well. We audience can ask the question in the neural network. Please, the audience are encouraged to ask the questions in the neural network. By the way, fine-tuning optimization techniques, I think maybe each team can, if you could explain what are the fine-tuning efficiency and the optimization techniques, improving the fine-tuning efficiency, if there are some specific techniques that you have used, please. So if any of the teams, if they have used any specific techniques.
I see Team Excellent. I think our colleague Wang has already put some explanations in the chat window. If you don't mind coming to the stage and then briefly introduce the fine-tuning techniques that you used with our audience as well, if you don't mind.
We use the layer norm tuning specifically for task 1. We directly fine-tune WiFo output head, and for the task 2, we use a 1D CNN adapter and to solve the problem.
Okay, thank you. Yeah, anybody else? Any other teams used any specific techniques for fine tuning or efficiency, please?
Hello, can you hear me? I'm Hao Xiangtan from 10checks.
Yeah, Go ahead, please.
Because the WiFo model has an encoder and a decoder. From the encoder, we can get the deep spatial and frequency features, and from the decoder, we can get the reconstructed CSI tensor. So for task one, the WiFo model just satisfied our task one. So I just unfreeze the decoder and fine tune it through the data, so we can get the grade and not that much parameters. And for task two, it's a classifier task, so we can use the special and frequency features, and we downsample and use an CNN, so we can get the two classifier result. And for task three, the correct answer I think is through the CSI data and the image. We can use the WiFo model to fine tune the WiFo model, or add LoRa to solve this problem. But since this is a competition and we can have that skill, I noticed that the camera is just that one camera, not changed. So we can take a little skills, just use a Euro model to I think to detect our object that we wanted, and then we can use like interpolation or reflection, and then we can get the real XY uh, that we want. And this is my idea.
Thank you. Thank you. Yeah, but it's an excellent idea. Thank you very much. Yeah, that makes sense. Any other techniques any of the other teams have used? I don't see any audience questions. Maybe another question about feature selection techniques. Again, I have put in the chat window. Wireless channels have specific characteristics. Maybe dynamic changes in the channel. So when you select the feature selection techniques which you use, are there some specific features that, are there some specific feature selection techniques that you see works well with these type of data from the wireless channels? Any specific feature selection techniques that you have used? Maybe all the teams can briefly describe the feature selection techniques, please.
I don't know whether Zero Grad you would like to jump in and briefly introduce the feature selection techniques that you use. I think just now for another question, I guess didn't have the chance to talk about your solution. Don't know whether you would like to jump in. Okay, maybe for other teams, whether would like to understand whether you thought about such techniques that you are using during the problem solving time. Okay, I don't know whether maybe colleagues from Boxun, Xuanyu, when you are doing the research, do you have such things in mind, or have you ever considered the feature selection techniques during your research? Or maybe whether we can
okay.
have some input from Prof. Tsai as well. I mean, when you are designing the problem statement, whether you have ever considered the feature selection techniques.
Yes, I think the feature selection is important for the adaptation on a wide range of various tasks. But in our challenge, the feature may be fixed. We use I understand it's a fixed feature, and our participants use this feature to solve different tasks by fine-tuning. It's different from that there are many features and we choose the best one. It's not that. I think this.
Yeah.
I see. I see. Mm. Okay. Okay. Yeah. In that case, maybe Bhushan, one question for you is regarding the results from the task. Do you see specific advances from the state of the art, the current research? Do you see specific progress in the results from published results versus the current challenge output? Do you see such advances, please? In the chat window, I've put in the chat window.
And also maybe Bhushan, apart from the contribution coming from these solutions that you received, where do you think that you are going further for the research? Maybe any inspiration provided by these solutions? Where do you want to develop more about this wireless model? If you may also share such experience with us.
Yes, I think the solutions I think the solutions from these participants is all very good for adapt our WiFo for these CSI related tasks and consider specifically concerning the fine-tuning cost. Yes, our challenge limits this fine-tuning cost, and I think for I think this their fine-tuning strategies have gave me many inspirations, and I think these techniques can be further explored for a better paper. Maybe I think.
Oh, very good. Thank you very much. And maybe such ideas can be the phase 2 of the competition. Maybe you can look at such techniques, fine-tuning, efficiency, optimization techniques, and fine-tuning could be the next phase of the competition. Thank you very much for the very nice results. Congratulations to the winners. No more questions. Thank you for the nice presentations and congratulations again. Back to you, Zhang.
Okay. Thank you, Ram.
Okay. Okay, thank you everyone. Thank you Vishnu for taking care of the Q&A session, and also PKU colleagues for the problem statement recap and also the solutions coming from the participants. Congrats again for your wonderful work. And I think throughout the interaction, I see that maybe we have further questions to be considered, and also the working directions for maybe second phase or even further. But anyway, thank you very much for contributing to this webinar and also the competition. And we have more sessions in the future. And also, please feel free to check the AI for Good program page, and also to select the sessions that you are interested in. Of course, for wireless foundation model, there's also a lot of work going on with our partners. Thank you again for proposing this problem statement. Thank you everyone for joining. See you next time. We hope to see you in the future. Thank you guys. Bye-bye.
Thank you. See you.
Bye-bye. Bye-bye.
Thank you for participating in today's AI for Good session. We hope you've learnt something new, innovative, and engaging in today's event. We now encourage you to continue the conversation on the live video wall in the neural network. Here you can ask questions, like and comment, share links, complete the poll, connect with interesting profiles, or speak one-on-one using the chat and video function. We invite you to explore the lobby, try the smart matching quiz, visit the virtual exhibits, poster boards, the e-shop, and build your personalized AI for Good program. Let's shape the future of AI for Good.